All right, we're looking at radical functions and transformations, making changes in graphs and equations, how they relate to each other. Now, specifically here, what I mean is if we have a function that's a more complex function, but we can relate it back to that basic square root function, we can use that knowledge to help us create the graph quickly and easily. And secondly, then, we want to look at how the domain and the range are affected by transformations and then make some predictions without even having to create the graph. All right. Now, the ones that we're going to graph here are going to be of this form, where we can recognize some of the transformations. All right, where we have a stretch factor inside or out possibly, and then a translation factor inside or outside the function. All right, so let's look at a couple of things here right now. Let's look at a graph here that we can make some changes on. If we have a graph here, this is just this basic square root function. Now, the way this software displays it right now, it says 1 square root 1x. But that's just, y equals square root of x. Now, we can make various changes to this, right? We can change that number outside that function, in front of that function, and that's going to be a vertical stretch, vertical expansion, or compression. We can do lots of other things here. Now, for this particular function, changing that number inside, multiplying by a number inside, it's hard to tell, but you're actually compressing it or expanding it horizontally there. And we're going to look at that a little bit later, how those two things are connected. But of course, you could also slide it one way or the other, and you can slide it up and down, right? And then when you have negative numbers involved in those stretch factors, that also turns into a reflection one way or the other, right? That way or that way. So we're going to look at that now, how you can use that knowledge of general type of transformation to work with specific things, specific radical functions. All right, so first let's tackle this. So you have a radical function here, this one up here, and you can look at it and decide how is that related to this basic square root function. Again, the basic square root function being this. Now, the basic square root part of that function is here, square root of x. But you have some changes that have been made to that. All right, you have this negative 3 out in front. You have this subtract 2 inside there. Okay, x has been replaced with x minus 2. And then on the end here, you've got this plus 4. And you have to think about how all those things affect the graph when we look at this. That negative 3 out in the front is going to represent a vertical stretch and a vertical reflection. Okay, so it's going to be a vertical expansion by 3. And it's also going to be a vertical reflection. Okay, it's going to be a vertical stretch by a factor of 3 and a vertical reflection. The fact that it's x minus 2 inside the function rather than x is going to represent a horizontal translation of 2 to the right. And then this 4 added onto the end here, that's going to represent a vertical translation of 4 up. All right, so you can use those ideas to try and create the graph of this. Now we're going to try a couple different methods to do this. One method is to transform some key points that you know on the basic square root function based on the transformations involved there, and then graph the final result. So if you know some points on y equals square root of x, right? If you know that 0, 0, 1, 1, 4, 2, 9, 3, okay, if those points are points on the basic square root function, we're going to think about how each of those points gets mapped on this transformed function based on the transformations, right? Based on our vertical expansion, our vertical reflection, and then after that our horizontal translation and our vertical translation. All right, so we got 4 things involved there. We're gonna make those changes. So let's work with one point at a time here. Let's start with that one, because that one's fairly easy. If we do a vertical expansion on that by 3, this is going to stay where it is, 0, 0. This one is going to, let's put brackets around everything here, see what we're doing. This 1, 1 if you do a vertical expansion, think about what changes here, right? The y values are going to change. And if we also do both these things at once, if we do our vertical expansion, vertical reflection here, each of those points is going to have their y value 3 times as much. So this one's going to be 1, 3, and it's also going to be negative because it's been reflected vertically. This one's going to become 4, negative 6. This one's going to become 9, negative 9. All right, because you've reflected it and you've expanded it vertically, stretched it vertically by a factor of 3. Now we have to apply the two translations we have here. Okay, now each of them affects a different coordinate, so I'm going to do them together here. All right, so I'll write some new points there. So this first set of transformed points was after our vertical reflection, our vertical expansion. Now we're going to do it after our horizontal translation, our vertical translation. This point 0, 0, which is the end point of that basic square root function, think about where that's going to go. If you go 2 to the right and 4 up, it's going to go 2, 4. That's where that's going to go. All right, we're going 2 to the right and 4 up. That's where our end point of this new function is going to be. The other ones here, we're going to take these transform points and think, okay, if we go 2 to the right here, we're going to have 3, and if we go 4 up, we're going to be at 1. And then this point, if we go 2 to the right, we're going to be at 6, and if we go 4 up, we're going to be at negative 2. If we go this last one here, if we go 2 to the right, we're going to be at 11. And if we go 4 up, we're going to be at negative 5. So then all we need to do is graph these points, and then we'll have our transformed function. All right, so we already graphed that first one there. That's going to be that end point. And then 3, 1 is right there. And 6, negative 2 is right there. And 11, negative 5 is right there. Now, and try and draw a nice smooth curve through this as best I can. It's going to keep going that way. The way I know that is because we could have put more points on the end here, right? I could have done 16, 4, and so on, right? More points than that, and it would have kept going to the right, all right? So that's the graph of this function using transformations working with the points, okay, by just transforming those points. Now the other way we can do this is to draw a series of functions, one for each step. So if we just make the changes one at a time to the equation, start with y equals square root of x, and then think about the order that we need to apply these transformations. First, we need to deal with the stretch and the reflection. So the first thing we're going to graph is y equals negative 3 square root of x. Okay, the reflection and the stretch. Normally this graph would be through this set of points here. Right, that's that same set of points. Whoops. So if I draw the original there, and then we think, you know, what's going to happen here first is it's going to be expanded by 3, something like that, and then reflected. Okay, so I'm not going to be able to do all the changes that way by stretching my writing there, but after those two changes, we're going to have it higher up here. So all these points are going to be 3 times as high, right? So it's going to be like that. That's y equals 3 squared of x. And then we need to graph underneath here because it's going to be reflected. This distance here just gets reflected down below. And this distance here just gets reflected down below. And then I can draw this, and that's going to be right there. All right. And then my last thing is just to worry about the two transformations there. So I can then take this one, negative 3 square root of x minus 2. X minus 2 is going to mean all those points just go 2 to the right here. I can draw the same thing in. And then the last change is going to be if I put that minus or plus 4 on the end. Right, and it's just going to mean all of these things, maybe I should change the colors to match here. That would have been a good idea from the start. Let me do that right now. Ready? Right now, they will all change. Bang. There we go, that's better. Maybe it would have been also good to include one in between here, because I did draw this one first, 3 squared of x. There we go. All right. So lastly, then I got to shift that one up 4, right? So each of these points is just going to go, boom, up 1, 4 there. That one goes up. This one goes up. And this one goes up. So whatever works better for you, right? If I draw this curve through here. And then I did have that other point there, but that's enough to get the rough shape of the graph. Either way there, right? So there's 2 different ways to create the graph. Now, I guess that looks like quite a mess there. So, if you're actually drawing this, maybe it's not a bad idea to either do the intermediate steps here really faint or be able to erase them after or something, right? Because in the end, you want just that final graph. Now, we're going to move on to something that's essentially the reverse of that. Here's a graph, and we're going to try and write an equation for that. All right, so we want to come up with the equation of that function based on what the shape of that graph is in our knowledge of transformations. All right, and we're going to do it a couple different ways here as well. And the first method we're going to look at is determining the stretch factor by comparing the distances on the graph and comparing to what we know should be the distances on the graph. All right, so we know this is the end point here. Normally, the shape of that graph is just that half a parabolic shape, right? It'd be 1, 1, 4, 2, and so on, right? That's the shape. And if this kept going here, we'd have 3, 9. So just knowing that shape and those distances, the fact that the first one at 1, 2, and then over here we're going to have 3, right? So we're going to compare that. We're going to look, if I was to go 1 over here, normally this is going to be up 1, all right? And normally 4 is going to be 2. All right, we can already maybe see what's happening here. Normally 9 is going to be 3. If you compare those distances to get that stretch factor, this is 6, 4, 2. Right? So this thing, if you're looking at it as a vertical stretch here, this new one here, this transformed function, is twice as tall as the basic one. So we're gonna take note here that this has to have a vertical stretch, vertical expansion times 2. All right, so that's one of the things that's involved. We can also tell that normally it opens to the right, and this one opens to the left. So it has been horizontally reflected. Okay, been horizontally reflected about the y-axis. And then the other 2 things are easier to see because that end point there on that function is 2 to the right and 1 up. So it means that we've got a horizontal translation of 2 to the right, and we've got a vertical translation of 1 up. So if we're going to write that equation after having done all that comparison like that, we can do it, because we can just say our function has to be, we have an x here, we need a 2 out in front, we need a, move that x for a second, we need a negative in there for that reflection, and we need a minus 2 to the right, and we need a plus 1 on the end here. Now notice I used a set of brackets in there inside that square root function. If you want it to be where that translation is applied last, that set of brackets needs to be there. It's not going to be the right thing to do this without these brackets and just write minus x minus 2 like that. All right, it's going to be the wrong direction. That's one equation that you could write for this. But that's not the only one, because I want to show you how we can look at it from another perspective here. And it has to do with this. Okay? It has to do with that vertical expansion. Now I looked at it first as a vertical expansion, but often you can look at it 2 ways for this particular type of function, just because of the shape of this half parabolic shape and the nature of that. If I looked at it horizontally, I'm going to get a different stretch factor. So I'm going to superimpose this over here. Normally you'd be 1, 1, 4, 2, 9, 3. All right, you have that set of points, and that's what that shape would be for for that basic square root function. But we can compare the distances horizontally in this case too, right? Because if we're looking horizontally, if we're looking at this as a horizontal compression, let me just do this so you can see here. What I could do is, or what we did first was, oops, not that, because we want to expand. Let's try again. Expanding it to fit it there, you know, my curve's not perfect, but we could expand it vertically to do that. Or we can compress this horizontally to do this. Now that's not going to be great either because my curve's not the right shape to start with, and I think I was a bit off at the vertex over there when I moved it. But essentially you can look at this two different ways here. You can compress it horizontally or expand it vertically. And you're going to get the same result here, and we'll look at why in a second. All right, but if we're going to compare the distances and figure out what this is, let's just use this second one. Normally we have 4, 2, but at this point, if we think of this as being compressed down to there, okay, the way I did it there, that compression factor there would be, okay, if I was to compress this here, that's going to be compressed down to 1, 2, okay? Normally it's 4, 2, it's 1. So it has been compressed horizontally by a factor of 1/4. All right? So you could do this, or it's a horizontal compression by 1/4. Horizontal stretch by 1/4. There's two ways to look at that. So if you look at it that horizontal way, to write the equation, instead of this 2 outside here, we're going to have something inside. Oh, that's a bit too big. We still need the negative inside there. Now if we want a horizontal compression by 1/4, we need to have a 4 inside here. Because inside that function it works the opposite, as I'm hoping you're aware of already. Alright, so that needs to be like that. Now if you want to know why that happens, let's just look at the square root function with just this scale factor, and we'll ignore the rest of it for now. So let's say we had y equals 2 square root x, and let's say we had y equals square root 4x, where the 4 was inside. So let's just look at that, ignore the other stuff, and see why this is going to work. Right? If you can write either one of these equations for that graph, we should be able to show that those are the same. All right? Now you can show they're the same if you take either one of these and try and change it algebraically to the other one. You have no doubt learned that working with radicals here, square root of two things multiplied, you can write it as those two square roots individually, right? If you have square root of two things multiplied, you can write it as those two square roots individually. And square root of 4 is a 2, right? And there's your function. It looks the same. Some of you may have thought of it when you worked with radicals in the past. You may have worked with or thought about it this way, that you can pull a perfect square out of there as long as you take its square root when you write it outside. If you pull that 4 out, right? If you're going to pull this 4 out of the square root sign, if you're going to take that thing out, which I'm having trouble doing, if you're going to take this out and put it out here, you got to write it as a 2, take its square root. All right? That's why those are the same. All right? Now I did tell you there's two methods we're going to use for this. Here's the other method. Work with the equation and substitute a point. Now what I mean by that is write the equation but use a variable for that stretch factor and then solve for that afterwards, right? Using a point on the graph. All right? Because we can write a few of the things right away, right? If we're trying to write this equation here, we know that it's going to be reflected that way and 2 to the right and then 1 up. So we know that. But what we don't know is the stretch factor. So let's say we're going to call it a vertical stretch. So we're going to use a variable there and solve for that. We're going to call that A, right? A is that thing. Now as long as we use a point somewhere else on the curve that we know for a fact, so we can either use that one, or you could even use this one up here, any one of those ones. Which one should I use? Let's use this one up here. So this is -2, 5. Right? We're going to substitute that point in for x and y, and then we're going to create an equation that only has one variable. So I could substitute in here for y. I can put 5, And for x, I can put -2. Right? And the rest I'm going to write all the same here. A square root negative 2 plus 1. If I work that down, a times square root of, oops, now I got to be careful up here that you don't think that that 1 is inside. That 1 is definitely outside, so let's be careful. So we have, this is -4, right? Don't want to take too long to do this, but I want to make sure we know what we're doing here. This is 4 underneath there, plus 1. Square root of 4, we've got a times 2 plus 1. And then we have a 5 on the other side. So the way you would normally write this is this, right? So 2a is 4, and a is 2. Now that's what we found the other way, right? The other way, by comparing the vertical distances, we found that that was 2. This is finding it algebraically by subbing in that point. All right, and then we know the equation's got to be, just fill it in for that a value that we put up there, 2, right? Replace that a value, and then write the rest. 2 square root x minus 2 plus 1, right? So you can get it that way as well. Now you could do exactly the same thing if you were looking at it as a horizontal stretch. You'd come up with that a quarter inside there. So if we did that, what we would have here is negative, we'd call it, well, we could even just say either way, you could leave the negative in and say negative b x minus 2 plus, oops, keep putting the plus 1 inside, it's got to be outside. You could do the same thing here of subbing in a point and just solving for this b value here. Whether you put the negative in or not is not going to make a difference. If you sub in that same point there, you'll find you get what you're supposed to get. So if we sub in here 5 and -2, and we work our way down the way we did before, right? Negative b there, square root, plus 1. And we need a bit more space. Let's create that. If you're going to work your way down there, you got negative b times -4 plus 1. So you have square root 4b plus 1 equals 5. So you have 4 equals square root of 4b. To solve that, you need to square both sides. So you're going to get 16 is 4b. Right? Squaring both sides. Square, square. Get rid of that square root sign. And then you have b equals 16 divided by 4, which is b equals 4, which is what we had there, right? Which is what we wanted it to be. Or not what we want it to be, but we already found that out before. We've got to have this as square root of, sub that back in for that value we had, minus 4 x minus 2 plus 1. So either way, you can solve it kind of algebraically by using a point substituted in, or you can do the first thing we did, which is compare those distances. If the distances are easy to see what they are, that's a lot easier than working through all those steps. So that's it. That is using transformations on the basic square root function to create graphs given the equation, or to write the equation given the graph. A couple different methods for each of those things. That's it.